And welcome to Lecture 11. Today we'll be covering momentum and the center of mass. Let's start with the definition of momentum. We represent momentum with the letter P. Momentum is a vector quantity equal to the product of an object's mass and its velocity. So, for example, if you have a 10 kilogram ball flying at 20 meters per second, it has 200 kilogram meters per second of velocity, 200 kilogram meters per second of momentum, parallel to the velocity. And a very good property of momentum is that, let's say we have some constant force F sub net, the net force on an object is constant, then the change in momentum of that object over time is the net force times the change in time. So for example, if we take our 10 kilogram ball from earlier and we apply a force that's pushing it in the direction it's moving of say 10 newtons for 10 seconds, then that adds 100 kilogram meters per second of momentum to it. And we call a change in momentum an impulse, which is represented by the letter J. And note that, again, these are all vector quantities. So momentum is conserved, and what that means is that unless something acts on the system, unless a force acts on the system, its momentum is not going to change. And remember Newton's first law, which said that an object's velocity is constant unless it's acted on by an external force. That's really, you can see how that ties into momentum here, because if an object has some momentum and there's no force acting on it, then it continues going with that momentum. And so its velocity doesn't change. And I said the word system. I'll be using that word a lot of times throughout this lecture. What a system is any collection of objects. As you can think, not every object is a point that is indivisible. For example, the ball from earlier, you can break it down into its constituent pieces, and that's still a system. So a system is any collection of point masses that come together and that it makes sense. Really, you can define a system arbitrarily. Like, we can define the ball as a system, but we can also define the ball and the earth as a system. And forces that are exerted by particles within a system on each other are internal forces, and they do not change the momentum of the system. While forces that act from outside the system on the system, those are external forces. So for example, let's take our system to be the ball. If an electron in the ball attracts a proton on the opposite side of the ball, that doesn't change the ball's momentum, because it's an internal force, not an external force. But if the earth pulls on the ball or I push the ball, those are both external forces, and they change the momentum because I'm not part of the ball system, and the earth is not part of the ball system. Let's move on to a very interesting example problem. Usually I write the example problems myself, but I found this lovely problem in David Morin's textbook, An Introduction to Classical Mechanics. It's a very nice textbook. It is based on calculus, so it's a bit higher level than this course, but I encourage you to buy it and read it if you have the time and are interested in going a bit deeper than how we go in this course. Anyways, the problem. So you're riding on a sled that is given an initial push and is sliding across frictionless ice. And snow is falling vertically in the frame of the ice on the sled. Assume that the sled travels in tracks that constrain it to move in a straight line. We'll say in the x direction for convenience. Which of the following three strategies causes the sled to move the fastest or the slowest? Strategy number 1 is sweeping snow off the sled so that it leaves the sled in the direction perpendicular to the sled's tracks, as we see in the frame of the sled. So that means that in the frame of the sled means that we perceive the sled to be stationary and that the snow is going perpendicular in that way. Make sure to get some good spatial reasoning. Think about what this would look like before you move on to solving the problem. Anyways, strategy number 2 is similar. We sweep the snow off the sled so that it's perpendicular to the sled's motion in the frame of the ice. So in the frame of the ice, the sled is moving. In the frame of the sled, the ice is moving. And strategy number 3 is we do nothing and let the snow pile up. Um, so let's define some handy quantities here. We'll say that the snowfall rate is x kilograms per second, which is also the sweeping rate. We'll say that we sweep snow infinitely soon after snow falls on the sled. Like the snow will fall on the sled, and then almost right after that we sweep it off. So it's basically a steady state. The mass doesn't meaningfully change. And we'll say that the sled has an initial velocity v sub naught, a mass of m, and a momentum of p. And note that sweeping snow off the sled doesn't exert a force on the sled. Well, it does, but it doesn't change the sled's momentum because the sled is always moving in the x direction. So if we sweep the snow off perpendicular to the sled's motion, then it can affect the motion in the x direction because that sweeping is in the y or in the z direction. So it won't affect the x direction, right? Because that's how vectors work, vector addition. So snow falling on the sled will change the mass of the system, though. Like, if snow falls on the sled for t seconds, then the new mass of the system is m plus xt, because we've added this snow to the system. And because ice is frictionless, snow that is swept off the sled continues to move. That's just something interesting to think about. It's not necessarily something you need to ponder. Okay, let's talk about the first strategy. So in the frame of the sled is stationary, so we see the snow moving backwards at a speed of v, or moving at a speed of negative v, where v is the speed of the sled at any time. Note that I didn't say v naught, because the speed of the sled changes. So falling snow will join the system and add momentum at a rate of negative x times v kilogram meters per second squared. So what that means is that, let's say the snow is falling and it has a speed of negative v, then that means that, we have x kilograms per second of snow. So that means that the momentum per second that's being added is negative x times v, because that's the mass of the snow over time times the velocity of the snow, if you think about it that way. And note that because v is changing, the amount of momentum that's added each time changes. So then we sweep it off, and it leaves the system, so it keeps going at the speed negative v. No, it doesn't keep going at the speed negative v. It goes at the speed negative v at t plus delta t, where delta t is the time between the snow falling and the snow being swept off the sled. So v of t and v of t plus delta t are actually different quantities. That's important to remember. Anyway, we sweep it off, and it takes negative xv times t plus delta t momentum with it. And negative xv times t plus delta t has a smaller magnitude than negative x times v of t. So what that means is that a large amount of negative magnitude falls on the sled, and then we sweep off a small amount of negative magnitude. So the magnitude of the momentum of the sled is still decreasing. Anyways, more snow falls, and if you care to set up the system, you'll see that because we're relating the rate of change of momentum to momentum, or equivalently the rate of change of velocity to velocity, we get an exponential decay. So that's that. In the second solution, in the frame of the ice, the snow has zero velocity, so when we sweep it off, it just kind of sits there. It keeps going in the perpendicular direction, but for our purposes, the perpendicular direction might as well not exist. So, because of this, when the snow falls on the sled, it adds some mass, but it doesn't add any momentum because the snow has zero velocity. And when we sweep it off, the snow still has zero velocity, so it takes zero momentum with it. And the sled's mass is basically constant because we're sweeping the snow off infinitesimally quickly. So basically the sled's momentum doesn't change, which means that the sled's velocity doesn't change because the sled's mass also doesn't change. And now the third solution. The mass of the sled just keeps increasing. It becomes m plus xt, where t is the amount of time that's elapsed. So the velocity of the sled is the initial momentum over m plus xt. Remember that in the frame of the ice, the snow has no momentum. When we were discussing the first solution, we were operating in the frame of the sled, because the sweeping was perpendicular to the sled's motion in the frame of the sled. But when we are dealing with the second and third solutions, we're discussing in the frame of the ice, where the sled is moving, and the snow is not. So velocity of the sled keeps decreasing here, but it decreases slower than the first solution, or rather the sled moves faster with the third solution than the first solution, because as more snow falls, the kind of proportion of new snow to old snow, like the percent increase of mass, keeps decreasing. Whereas when snow falls on the first sled, it's always the same percentage, m plus x times delta t, where delta t is the time it takes for us to sweep the snow off after it falls. So because of that decreasing percentage here, the third solution is faster than the first solution. So the first solution is slower than the third solution, which is slower than the second solution. And if you think about it, in the second solution, from our perspective on the sled isn't moving and the ice is moving backwards, right? So if we're sweeping the snow off perpendicular to the sled's motion as we see in the ice, then that means that if we see the sled to be stationary instead of moving like it is in the ice frame, we're actually shoving the snow backwards. So it's almost like you're pushing the snow backwards to move the sled forwards, if that makes sense. Anyways, I hope that was a fun problem. I suggest, if you have experience with calculus, that you set up the differential equation for the first solution and plot out that function and see how it compares to the third solution. Like, plot out the velocity as a function of time for the first, second, and third solutions and just see the difference. That'll be an interesting exercise. Anyways, moving on, let's define the center of mass. So let's say we have a system, right? A system of objects. The way we define the center of mass is the center of mass is a point that corresponds to the weighted averages of the positions of all the objects that constitute a system. So if we look at this first equation here, we have big M times big R is equal to the sum of M sub I times R sub I. So big M is the mass of the entire system, and big R is the position of the center of mass. And basically we're adding up the mass of all the constituent particles times their positions to get a weighted average. That's how weighted averages work, if you remember from math class. And note that if we take the time derivative of this expression, then we get that the total momentum of the system, or the momentum of the center of mass, which we can denote by big P, is equal to the sum of the constituent momentums of the system, or the momentum of each particle, right? M sub I times C sub I. I'm using the subscript I to indicate a summation over an index. Like if we were to expand this, we could denote the first particle as particle 0, and the second particle as particle 1, and the third particle as particle 2, etc. Since we start counting from 0. So the I is just a placeholder for the particle number, and it means that we're just summing over every particle in the system. So basically the momentum of the system and the momentum of the center of mass is the sum of the momenta of the objects that constitute the system. So yeah, that's a good thing to know, because it means that we can represent the system as just being a point mass concentrated at this one point, the center of mass. So let's do an example problem. I hate to give you this kind of problem because it's really just brute force computation, but let's find the location of the center of mass of this system. So we have at the point 1, 1 a 10 kilogram mass, at the point 2, 4 a 30 kilogram mass, at the point 3, 2 a 40 kilogram mass, and at the point 4, 3 a 20 kilogram mass. So plugging into the formula from earlier, we get that big M times big X, where big X is the X position of the center of mass, is 10 times 1 plus 20 times 4 plus 30 times 2 plus 40 times 3. Those are the X positions of each of the masses, and each of the masses is mass. And then big M times Y is equal to 10 times 1 plus 20 times 3 plus 30 times 4 plus 40 times 2. And big M is equal to 10 plus 20 plus 30 plus 40, that's 100. And so 100x is equal to 270, so x is equal to 2.7, and the same for y. So that's where our center of mass is. And let's do another example problem. Let's say we have a balloon in deep space at rest, and the balloon pops. Let's figure out how the center of mass of the balloon moves. So let's think about kind of what constitutes a balloon. A balloon has, the rubber wrapper kind of thing, and the air inside it. And the balloon is in deep space, so we're going to assume that there's basically no external objects that can exert a force on it. So when it pops, technically everything in the system is still there, it's just moving with a new velocity. But the point is that because no external force is acting on the system, since the balloon is in deep space, the center of mass doesn't move. The total momentum of the system stays the same, even if the momenta of the constituent particles are changing, right? Like an individual air molecule will change its motion when the balloon pops, but the balloon is still going to keep its center of mass at the exact same point, because there are no forces acting on the balloon system. So yeah, that's a good thing to know about center of mass, and we will come back to the center of mass when we discuss collisions in a couple of lectures. Anyway, thank you for watching this lecture. As always, if you have any questions, please feel free to come to Office Hours, and see you next time.